So far, we have studied propositional logic, where the basic units are statements that are either true or false. In this video, we're going to be looking at statements involving predicates, as well as quantifiers, our universal quantifier and our existential quantifier. Sometimes the quantifiers have nothing to do with the equivalence. So, for example, we could have the statement for all x, if p of x, then q of x, and for all x, if not p of x or q of x. These are logically equivalent, but we've already shown that the statements if p then q and not p or q are always logically equivalent. So the quantifier and the predicates don't actually affect this, but we will see examples where the quantifiers and predicates will play a big role. So let's look at an example here. Suppose we have a claim all square matrices are invertible. So symbolically, we might write for all A. So A would be our square matrix, or excuse me, our matrix here. If S of A, then I of A. So S of A is the predicate that A is square, and I of A is invertible. So this says for all matrices A, if A is square, then A is invertible. And so the question is this statement true? To show a universal statement is false, it is enough to find one counterexample. So the example here, this is a square matrix, 1, 2, 2, 4, but we could show that it is not invertible. Therefore, it is not true that for all A, if S of A, then I of A. And how did we show that? We found that there exists an A such that S of A and not I of A. So you could see the equivalence of these two statements, or hopefully, sort of follow the idea of the equivalence of these two statements. We can negate a for all statement by giving one counterexample, a there exists statement. So some quantifiers and negation here. To negate the for all x p of x, we can show there exists an x such that not p of x. And to negate the there exists an x such that p of x, we would show that for all x, not p of x. The other thing we want to talk about here is the fact that the order of our quantifiers does matter. So let's just see an example here. Suppose A is an n by n matrix and consider the statement for all B, there exists an x such that A times x equals B. So this means that for every vector right-hand side B, there exists a solution x to the equation AX equals B. This certainly could be true. It depends on the specific matrix A, but if A is a given n by n matrix and B and X would be vectors in Rn, then there are certainly some matrices where this would be true. If we reverse the order of the quantifiers and write, there exists X such that for all B, AX equals B. So what does this statement mean? There exists a vector X such that for every vector B, AX equals B. And that is not true for any matrix. There would not be a matrix such that we could find some vector where for every vector B, AX equals B.